5.1a wants us to set up a trigonometric ratio and solve for a side length. So here we have a tanker that sails due west from a port at 1 p.m. So here's the port that they're starting off, and they're going due west at 1 p.m. at a steady speed. So they're going this way. At 2:15, the bearing of the lighthouse from the ship is 37 degrees. So they've actually traveled from here to this point. And the lighthouse found the bearing with the ship, which is right here. The question in part A is this. If the lighthouse is 18.3 miles due north of the port, so it's right here, how far out is the ship at sea? Well, from what they said, the ship is going to be right here at this point. So what they want us to find is this length right here. Now, this is a right triangle, so we can use Sohcahtoa. And if we know right here that this is a perpendicular that's been dropped at 37 degrees from here to here, we can find this missing angle. 90 degrees minus 37 will give us 53 degrees. So we know this angle right here is 53. So knowing this relationship, and that's a right triangle, we can actually use Sohcahtoa. So we need to figure out which one to use. So remember Sohcahtoa, sine is if we have opposite and hypotenuse, cosine if we have adjacent and hypotenuse, tangent, opposite and adjacent. So for this angle we go straight across, this is called the opposite side, and this is the adjacent side. The hypotenuse is always a side right across from the right angle. So we have opposite and adjacent, therefore we would use tan. So we can write the tan of 53 degrees is equal to 18.3 over x. Now when we solve it, we want x to be on the top, so we can algebraically move that. All we need to do is, it says 18.3 divided by x, so we would just multiply both sides by x to get that. And when you do it, the x's would cancel out. Now the tan of 53 is just a number, so make sure your calculator is in degree mode and type in the tan of 53. You'll find that this value equals 1.327. Now to get x by itself, we're just going to divide both sides by 1.327 and see what we get. When you do that, you're going to get that x is equal to 13.79, and if we do the appropriate label on this, we're talking about miles. So the ship is actually 13.79 miles out of the port. 5.1b wants us to set up trig ratios and solve for angles. Now this question here really could have been an A or B. It's not as specific, but here's what they want us to do. Consider the triangle JBM here at the right. They want us to find the sine of M exactly and the tangent of B. So let's do that first. The sine of M is just having us remember what sine is. Remember, sine is it's opposite over hypotenuse. So find angle M, which is right here, and you're going to find the side that is opposite and the hypotenuse. So the value of sine of M is 15 over 17, and that's the exact answer. We don't need to do anything else. Now the next one is the tan of B. So to find tan of B, we need to find angle B. And remember, tangent is the TOA, so opposite over adjacent. Here this is the opposite side, and this is the adjacent. So tan of B would be 8 over 15, and that's the exact answer. Now part C wants us to actually find the measurement of angle B. So notice the difference in the notation. That's just the tan of B. Here's the measurement. Well, angle B is embedded in the word tan. We can actually solve for angle B, and all we need to do is to get the word tan out of here. So remember, all you do is to get rid of tan, you take the tan negative 1, or the inverse tan of 8 over 15. So the measurement of angle B is equal to tan negative 1, 8 over 15. And when you put that in your calculator, you're going to get that the answer is 28.1 degrees. Now remember, when do you hit the negative 1 button? Whenever the variable you need is embedded in the word sine or tan or cosine, that's when you do it. Otherwise, in an example back up here, you just hit the regular tan button because it's the tan of that number. For the next two questions it says, assume you have a ladder that is 12 feet tall. Here's the first one. If the ladder is placed against a wall, so its base is 2 feet from the wall, find to the nearest degree the acute angle the ladder makes with the ground. So let's do a sketch for this. So if this is our wall, and then we're going to put the ladder against the wall, one thing we know, they said the ladder is 12 feet long. And it says here that the base is 2 feet from the wall, so this right here is a 2. Now, you have to keep in mind this wall, assume, and it's very true to say, was built at a right angle. So here we have a right triangle. What they want us to find is the acute angle the ladder makes with the ground. Acute means less than 90, and the one that's here with the ladder and the ground is here is the green angle. And let's just call that angle X. So to find it, you want to figure out the best measurement. What we could do for this is we have this angle X. So we don't know this side, but we do know the adjacent side and the hypotenuse. So adjacent and hypotenuse is the ca, or the cosine. So what we would do is find the cosine of X is adjacent, which is 2, over 12. Now remember, when the variable is embedded, all you have to do to solve it is find the measurement of angle X is going to be cosine -1, or inverse cosine of 2 over 12. And when you do that, you're going to get, the answer will be 80 degrees. Now this next question, it says, suppose the base of the ladder is x feet from the wall. Find an expression for theta, which is that acute angle. So let's just adjust our drawing for a little bit. So there's the building, and then here's our ladder. The ladder still is 12 feet. But what they've said this time is we don't know the distance. The ladder is from the wall. This is x. And they want us to call the angle theta. So we'll just call this theta. Now I'll tell you, we're not going to get a numerical answer. We're just going to basically set up a formula. So when you look at this, what side lengths are labeled? Again, for this angle, we have adjacent and hypotenuse. So let's just write the cosine of theta is equal to the adjacent side, which is x, over the hypotenuse of 12. Now, they do want you to find an expression for just theta. They just want to know the angle. Well, the angle is right here. How do you get the word cosine out of there? What you would do is you would say the angle is equal to the cosine -1 of whatever x is over 12, and that is the answer. 5.38 wants us to set up a law of cosines formula and solve for a side length. So here we have a surveyor wishes to find the distance between a public marina and a private pier. So it looks like it's a distance right here on this picture is what they want to find. His measurements are shown at the right. What is the distance between those? So when you look at this, we know we cannot use Sohcahtoa because there's no right angle. Maybe law of sines or law of cosines would work. Actually, law of sines would not work on this, only law of cosines. So we want to find this side length, so we need a side angle pair, which is right here. So let's start the formula with this side length and fill in the other two. So it's going to be x squared equals 300 squared plus 200 squared minus 2 times the 300 and the 200. Remember, this is law of cosines, so it is the cosine of the angle that matches up with our side. Because remember that this side and that angle have to be partners. Now the trick here is just to simplify. So I'm going to go ahead for simplify. I'm going to do these exponents here, and then I'm going to multiply this entire thing together. So let's go ahead and do the first step of simplification. So when you simplify, 300 squared is here, 200 squared is here. I multiplied the 2 by the 3 and the 200 and got a negative 120,000, and I did the cosine of 55. Now I'm going to type in these two here to multiply together, so the answer will be negative, and then add these two for the next step. So when I do that, we have 130,000 minus this negative value. Bring these two together and get this value. We're going to wrap the problem up and solve for x, so I have to take the square root. When you do that, you're going to get that x is going to be approximately 247.3. And we're talking the distance here is in meters, so I put meters as a label, and we're done. Learning objective 5.3b is to set up a law of cosines and then solve for the angle. I do not have a specific example for this. If you would want one, I just recommend going back and looking at the homework or going to the textbook and trying some extra practice that's picked in there. If we look at 5.5a, set up the law of sines formula and solve for a side length. Here's the first example. Find x in the triangle below, which is this side. round your answer to the nearest tenth. So when you look at this, law of sines works well. We have this angle and its matching side. And we actually have a second angle right here. And if we go straight across, its matching side. We only have one unknown, so law of sines works well. Now law of sines, you can put the angles on the top or the sides. Since the side is unknown, I'm going to put the side on the top. So let's do x over, it's the sine of the angle value, so the sine of 15. That's going to be equal to 5 over the sine of 140. Do not forget to put the word sine here, it's very important. Now what we need to do is get x by itself, but it's being divided by the sine of 15. I can keep it in this format right now, and I'm just going to multiply by the sine of 15 on both sides. So when I do that, what's going to happen is this becomes one big problem there. The sines of 15s cancel out. So all I need to do in my calculator is take 5 times the sine of 15, get the answer, and divide it by the sine of 140. And when I do that, here's what I get. Is this value here. Now they do want us to round to the nearest tenth, which would be this first decimal place. So rounding to that would just end up being 2.0 is the final answer. Now this next one, we have triangle ABC. We know the measure of angle A, the measure of angle C, and side length C. They want us to find side length A. So let's actually sketch this image first. And I don't know if it's drawn to scale, and that's okay. But I'll try to be somewhat realistic. So I'm going to call this guy right here angle C, and that's 70 degrees. Now straight across from it is its side length, which is 14. And then angle A, let's go ahead and call this one angle A. That's 56 degrees. And they want us to find side length A, which should be right across from it. So right now I do have enough information for law of sines. So what I would write is, let's do the side lengths on the top. So we would do A over the sine of 56 degrees is equal to 14 over the sine of 70 degrees. I'm going to go ahead and change these to decimals this time just to do it a little differently. And when you do, here's what you get. It'll look like this when we change these two to decimal answers. Now it's A divided by that, so let's multiply both sides by the 0.829, and we'll multiply this by 0.829. And when you do that, what you're going to get is 12.35. So side length A is about 12.35 in length. 5.5b wants us to set up the law of sines formula and solve for an angle. So here we have triangle XYZ. We know the measure of angle X and its side length, and we know side length Z. So what we have here is finding all the possible values of measurement of Z to the nearest tenth of a degree. So let's sketch the image first of what we think it looks like. So let's do this. So this is a possible scenario where angle X is 43 degrees and there its corresponding side length. Here's angle Z that we don't know and its corresponding side length. Now be careful, for triangle congruency, this is an angle side triangle. Remember, when you have an angle side, you have to be very careful. There's up to 2 possible triangles. So even if the problem doesn't prompt you to find all possible values, you must need to realize with angle side, there could be a second triangle. And what could happen is this side length here of 7.5 could actually swing and be tucked in right here. So let's draw that second triangle. So this is what it looks like. Again, all I did was take this side length and I brought it in this way, so it went this direction. So we have an acute triangle and an obtuse. I'm not sure if the second triangle is valid, so let's go ahead and do the math and solve it and see if it works. Now when we do this, you're going to notice we have an angle side combo and a side and an angle. Now we don't know the angle, so let's start by putting that on the top. I'm going to do the sine of Z over 9 is equal to the sine of 43 divided by 7.5. So let's go ahead, and I'm actually going to try to get the sine of Z by itself. Don't have it divided by 9. I'm just going to multiply both sides by 9. So the 9's will cancel. What I'm going to type in my calculator is a sine of 43 and hit enter, and then times that answer by 9, then divide by 7.5. When I do that, I'm going to get that the sine of Z is equal to 0.818398. Now remember, to get z out of the word sine, all I need to do is come in and do the measurement of angle z will be the inverse sine of this value that I just found. And when we do that, we're going to end up getting that the angle will be 54.9 degrees. And that seems logical with our picture. Now we need to test, does this second triangle here actually exist? How do you find it? Well, keep in mind, this right here was this original side length, but we decided to tuck it in this way. So if this angle came back at 54.9, it means this one is also 54.9. But what I really want to find is this angle right here. These two angles sit on a linear line, so all I have to do to find the second possible angle is take 180 degrees and subtract from it my answer of 54.9 degrees. And when you do that, what you're going to get is 125.1 degrees. Now, is it possible? Can we have 125.1 here and add to it 43 degrees and still have room to make a 180 degree triangle? Yes, we can. So this problem actually has two answers, here and here. If this is not possible, where it would exceed 180 degrees with just two angles, you would have to cross this out and you cannot count that as an answer. 5.5c, we need to find the area of a triangle using the sine-based formula. So here we have an area of a triangle they want us to find. It's not a right triangle, so technically I cannot use 1/2 base times height. But we have a really great trick. Remember, area is 1/2 AB, the sine of C. What that means is you're going to take two sides and you take the angle created by those two sides. So in this case, we have the two sides and we have the angle created by those two sides. So the math on here is very clear cut. 1/2 times 4 times 11. Be careful, now it's the sine of 110 degrees. When you type that in, you're going to get 20.67. It's centimeters squared because we're finding area. The last two problems in 5.5d want us to determine when to use the right triangle trig, law of sines, and law of cosines. So let's just piece these problems together and figure them out. Here we have two sightings 80 feet apart are taken to the top of a canyon wall. So someone is standing here and someone is standing here and they're looking at the wall. The angles of elevation are shown. Remember, angle of elevation, they're looking this way, their eyes elevated up to create the angle. The question is, how high is the top above the canyon floor? So they're right here, they want to know this height. So the question we need to find basically is, what is the height of this wall? Now, what I like to do with this problem is, because this is such a small skinny triangle, is redraw it and kind of exaggerate it a bit. So let me show you what I mean. So what I did is made more room in here, and let's relabel the data. So right here is a 38 degree movement. This one right here is 35.3 degrees. And we know that this length right here is 80 feet. Now we need to find the height of this wall. And there's a variety of ways to actually do this problem, so you just have to kind of piece it together. Now the first suggestion I have for you is to try to see how many of these angles you can complete. And I will tell you, you can complete every single missing angle. So let's talk about how you would do that. This right here, these two angles, right here and here, make up a line. So if that's 38 degrees, I can easily figure this out by subtracting it from 180. And when you do that, you're going to get that this angle here is 142 degrees. Well, if I have this angle and this angle, I know this little one up here has to round it out to be 180 degrees for the whole triangle. And when you do that, this ends up being 2.7 degrees. The last one we can do, if this is 90 and this is 38, I can look at just this right triangle. I can get this third angle. What I'm going to do is I can actually subtract that from 180, those two, and you would end up getting that this would be 52 degrees. So now there's a variety of ways you can do this. This is actually a two-step problem. What I recommend is doing law of cosines first and then wrapping up with either law of sines or Sohcahtoa. Our ultimate goal is to either use this little right triangle or this big right triangle, either one of them. So if we use this little right triangle, I need to find this side length. If we use the big right triangle, I need to find this side length here. What I'm going to go ahead and do is choose to find this side length right here. And let's just call that side length A. So side length A, if we find its matching angle, is going to be right here. So those two match up. But we already have another pair that matches. This 2.7 degrees matches up with the 80. So we can write our formula like this. I don't know side length A, but I know it goes with the angle of the 35.3, which is right here. So the sine of 35.3. And then that's going to be equal to the side length of 80 divided by the sine of 2.7 degrees. So to simplify this, I'll put this in my calculator and get the answer, and then I'm going to come on in and multiply by the sine of 35.3. So here's what we have when this is simplified. And this is A divided by the sine, so let's go ahead and multiply. And I'm just going to show you that I'm going to multiply this sine by 35.3 degrees. And then that's going to give us that side length 8 is 981.365. So I just discovered that I know this side length here. So let me just redraw this triangle for you down here so we can see it better. So here's what we have. Is this triangle? Well, I need to find this side. If I look at 38 degrees, this is opposite and this is hypotenuse. So let's just go ahead and finish this off. Let's do the sine of 38 degrees is equal to x over 981.365. All I need to do to solve this now is to move the 981 over. So I'm going to multiply this side by 981.365 and do the same thing over here. Clearly when we do that, what we're going to see happen is that these will cancel. So let's simplify this in our calculator. And when we do that, we're going to get that x is equal to 604.188. Now keep in mind this is not the only approach. What I could have done differently is found this side length here by using the law of sines. And if I found this side length, then I could go ahead and use the Sohcahtoa. I would use the sine of this angle and use opposite and hypotenuse on that. And you'll get the exact same answer. Now for this example, we are dealing with a compass, so I recommend sketching the compass on the paper and drawing the picture on top of this. And assuming we start right here in the middle. So here's the scenario. An airport controller notes from radar that one jet is 12 degrees west of north. So the airport controller is right here. Now the one jet he's looking for, it says here, is 12 degrees west of the north. So there's a jet that's moving 12 degrees west towards the west of the north. So the jet is actually going 12 degrees this way. So if you sketch that 12 degrees, we're talking about right here, and that's where we're going to put the jet, and that's the 12 degrees. They also say here it is 20 miles from the airport, so we're going to label this side length as 20. Now this plane is flying toward a private plane, and that private plane, it says here, is 27 miles directly north of the airport. So if you go directly north of the airport, 27 miles, this is where the private plane is, and I'm going to call that P. And we can label this side length as 27. So the question is, how far apart are the planes? What they want to know is this distance right here, and we'll just call that x. So the sketch on this one is probably the trickiest, but if you look on how to solve it, in the case for this one, Sohcahtoa does not work. There's no right angle. Law of cosines on this one actually does work quite well. Unfortunately for law of sines, there's not enough information, so there is only one option. So for law of cosines, what we want to do, we need this side length and then its corresponding angle, and then the other two sides. So let's set up the law of cosines, which would be x squared equals the two sides squared, so 20 and 27, minus 2 times those two sides. And remember, it's law of cosines, so we wrap up with the cosine of 12 degrees. Let's go ahead and simplify these two values and this one right here. And when you do that, we're going to get these two values. I did 2 times 20 times 27 and got this, and the cosine of 12 is this. Now be very careful. If this cosine value right here in my calculator came back as negative, if I had to multiply this negative number by another negative, this would then change to positive. But in this case, we have a negative 1080 times this positive value. So let's multiply these two, and I'll also combine these two in the next step. So here's what we have, the 400 and the 729, and then these two values multiply to that. Let's subtract these two to get 72.6 and wrap it up by getting x by itself. Don't forget to come in and take the square root. Therefore, x is going to be 8.5, and we're talking miles and how far apart the two planes are from each other.